All right. So today we're going to do a quick introduction to what will eventually be our study of integrals. Okay. But for now, we're just going to phrase everything in terms of an example. And right after this class, I'll send out the worksheet and people can take a look at that. So the name of this lecture, because we're dealing with the example, is just how far did we go? So the setup is this. We're traveling somewhere and we know our velocity over time. So we have some curve, which is drawn in blue, and we have, at time t over here, we're traveling at v, say maybe miles per hour, if that's familiar to you. So we might ask the very natural question, which is the name of this lecture, how far did we go? So from time 0 to time t, how far did I actually travel? And if the velocity curve is a constant, we already know how to do this, right? Because we know that distance equals rate times time. So in that case, if the velocity curve is a constant, I can draw that real quick. Well, that's supposed to be a straight line. If the velocity curve is a constant, then the distance rate times time is just the area, which I'll do purple, the area under this curve. Okay, so that's sort of our best guess right now for how far we traveled. It's not this purple area, but it's the area under our original blue curve, which I'm now doing in green. Right. But the issue is that we can't do something as simple as distance equals rate times time anymore because the velocity is not constant. And in the real world, that's usually how it is, right? We don't just get in our car and then immediately we're at 30 miles an hour and then we stay at 30 miles an hour for our entire trip to the grocery store and back. No, we get in our car and then we have to accelerate and then maybe we hit a stop sign or we hit something else. So there's some function that tells us how fast we're going at any given moment, and we have to account for that variation. Okay. So we might do the natural thing. Well, beforehand, we use this rectangle because we knew distance equals rate times time over a constant. But if we assume that in these small intervals of time that I've drawn in these red rectangles here, if we assume in these small intervals of time that we're constant, then we get each a rectangle for each of our approximations. So here, I'll just highlight some of the things that I've already written. Say at the very bottom there, it's 25 miles an hour, and then I've divvied up my trip of 5 hours into 1 hour each, right? And then I'm saying that at my first hour, I'm just going to assume that I'm driving at a constant rate. And I know I'm not, because my blue curve is not constant over the first hour. But I'm just going to assume that. And then here, after the hour ends, I'm going to take another measurement of my speed, and I'm going to say, oh, well, that's faster. So let's change our approximation. So now I'm traveling this fast, right? So maybe this is like 30 miles an hour or something. And then I do that every hour, and I get a new approximation. And then I assume that over that hour, I'm actually traveling at a constant speed. Of course, this is an approximation, but notably, this is a better approximation than if I just assume the entire time I'm going at a constant speed. So if I assumed that because I was at the very beginning, I traveled at 25 miles an hour, then I just get the area of this rectangle here, right? But of course, the area of all the red rectangles is larger than that, right? We can see that just visually. So the red rectangles is closer to the area of under the actual blue curve than is the green rectangle, right? And that has to do with the fact that we're adjusting our approximation more frequently, okay? So before I move on, does this setup so far make sense? What we're trying to get from this setup and how we're approximating so far with these rectangles? So just give me like a yes in the chat or all good or whatever you like. Okay. Dishun, Aaron, Michaela are good. Awesome. If you have a question, please be sure to ask it. Alex and Yuling are good. Brett's good. All right. I think that's everyone. Okay. So one more thing I'll mention before moving on is that over each of these smaller rectangles, we can still do our approximation, right? So I have this purple area here, and the purple area, I know I can calculate easily because it is a rectangle. So I have the bottom here I said was an hour. And then over here I said I'm traveling at 25 miles an hour. So over a rectangle, we can just do distance equals rate times time. So of course I know I traveled 25 miles. Okay. And I can do the same for each of these other rectangles. Okay. So that's what I'm going to do. So if I want this whole purple area now, then I have to take the sum of the areas of the rectangle. So sum meaning I have to have plus signs in between the areas of the rectangles. Right? So the formula to the right there, it says purple area equals, and then it has all these terms and they're all summed up. That's because I'm literally just adding each of these rectangles size. So the first term, V naught delta T, I'm saying, well, in the last slide, we called it an hour, but let's call it delta T. Let's call it delta T for change in time. So however long I wait before I take my next approximation. And then at the time I take my approximation, I'm traveling at V0 miles per hour, okay? So just as we had in the last slide, but now I'm writing them as V0 and delta T instead of 25 miles an hour and 1 hour. So now I just have V0 times delta T is the area of this rectangle right here. Okay, but if I keep my delta T constant, so if I approximate at the same interval every time, then my my rectangle width is always the same. It's always delta T. But of course, my velocity is changing every time. So first I do V0, but then I have to do V1, V2, V3, V4, right? Because the actual velocity is going up. So when I take my approximation, it's different every time. So my purple area is just this sum. Okay. I think we'll do one more slide before we break again for questions. Okay. So the question you might see with this previous slide is, well, this is still an approximation, right? It's good, and it's definitely much better than the one rectangle we used earlier, but it's not a perfect approximation, okay? And we might ask, well, can we get a better approximation? And the answer is yes. We can always get a better approximation. So now instead of taking the delta T that was this large, I'm taking half that, okay? So you see I've subdivided my rectangles. I now have twice as many rectangles here in red, okay? And the purple area is the same as before, but now with these new rectangles, I have more area because it's a better approximation at every point, at each point. So each of these new approximations is picking up this little orange area that I didn't count in the previous slide. So I'll just draw one. So when we subdivided this rectangle, for example, it adds this little area here, right? Now the subdivided rectangles still give you that purple area in this rectangle, but we get that extra bit on top. And you'll notice that the difference, like the white area here between the rectangles and the curve is smaller, right? Because I took more of that with my approximation. So my approximation is better when I take smaller steps. So that's what this slide is telling you. New area counted with smaller delta T is better. And you'll notice the white area again between the curve itself and the rectangles is smaller. So we're getting very close to the actual distance that we traveled. All right, let's take a break here. How are we doing? Any questions? All right, Daeshun's good. Jerry's good. Michaela's good. Aaron's good. Brett's good. And Alex is good. And Yuling is good. Awesome. Great. Okay, so this is fairly conceptual so far. We haven't done much math, but this is really how we want to think about this to start. Calculus can be very conceptual, as you guys know. And I think, I can't remember who told me this, but I think it's true that Newton actually invented calculus in a pandemic. So this is very topical that we're really learning this much during the pandemic. All right, so velocity being positive, right? That means that we always talked about how speed is an absolute value. Speed is always positive. I can't travel at negative speed, but I can travel at negative velocity because velocity is speed with a direction. So remember, I gave the example that if I'm standing here and I'm looking at how fast I'm traveling in this direction, if I walk backward, then that would be negative velocity. So if we assume that we're traveling with the direction that we're pointing in, then we say velocity is positive, just as a recap. So if velocity is positive, the total distance traveled is just the area under the curve. So that sort of makes sense with what we were saying, right? Because we were saying that how far we went, as long as we're measuring velocity in a correct way, is just that area under the curve. So it fits with our idea. But the difference is, and I think maybe I say this on the next slide. So if velocity can be allowed to be negative, having some technical difficulties, hang on. If velocity can be allowed to be negative, come on now. Wonderful. My pen is not working again. I just fixed it. Now it's doing this again. I'll just say this in words then. If velocity is negative, then I can travel in a positive direction, and I've traveled 10 feet, and then I stop, and I turn around, and I go in the other direction, and I travel another 10 feet. But that would tell me that I'm exactly where I ended up. So the area under the curve counted with sine would be 0. But if I just count the area under the curve without sine, then it would be the total distance I traveled, which was 20 feet when I walked forward 10 feet and backward 10 feet. So we're asking the question, what does it mean when the velocity is negative? It just means we're going to count this area with sine instead. So we're going to define some terms that help us make sense of this a little bit more and be precise about what we're saying. So we'll say the change in position is given by the area above the x-axis minus the area below. So again, counting with sine, that's what I mean. And distance traveled, of course, is just given by the area above plus the area below. So now we don't care about sine, we just add everything. So there's a difference between change in position and distance traveled, as we saw in the walk forward 10 feet, walk backward 10 feet example, because the change in position is 0, right? But the distance traveled is, of course, 20. Okay, let's see if my pen's working now. Nope. Excellent. Okay. So you might ask the question, well, we made a very subtle assumption in the first slide, and I'll go back just to show you. We made a very subtle assumption. We said, what if we measure our velocity at the start of our time interval and then we assume that for the rest of the time interval it's constant? Well, we could have just as easily said, what if we measure our velocity at the end of the time interval and assume that it was the same for the previous hour, right? So we address that here when we talk about left and right hand estimates. So this is called a right hand estimate, where I take my estimation toward the end of my time. Okay, so this is a subtlety, but it turns out that these notions are going to be, they're going to give us the same idea for an integral. Okay, I don't think this is as prevalent in the course material anymore, but there is a notion of the accuracy of the estimates, which I thought I would mention. So if you're operating at a closed interval, so say you start at time 0 and then you end at time 10 exactly, if your function is only increasing or only decreasing, so velocity but you're accelerating or you're just decelerating, then the difference between your left and right hand estimates is a function of the step that you take, so delta t. So notably, as I let delta t go to 0, as delta t goes to 0, the whole right-hand side goes to 0, right? But if the right-hand side goes to 0, that means that the difference between my estimates gets very, very small. So in other words, as my approximation becomes closer and closer, then the left and right-hand estimates will not disagree. They will agree very nicely. Okay. But if you wanted to compute the difference between these estimates for a particular time interval over which you're taking an approximation, then this is how you would do it. And I think there's one question on the worksheet about that, but I don't think there's anything else because it's not too important. All right. I think that's it. Any questions about this? If we're good, just let me know in the chat.